will see that in the viscous tab now, there is this turbulent mixing line model enabled. So we set the turbulence model for the case. Were you all able to set the mixing line? No? Do you need any help? So then if you are stuck here, then I move on and then you cannot run the case, could be a problem. And just tell me if you need help. Then next we should set the boundary conditions. So now we have the grid, the fluid, the turbulence model. For our domain, we need to set the boundary conditions. So total pressure, total temperature at the inlet, static pressure at the outlet, and then slip wall for this section over here, and symmetry on the top. So first of all, I don't know why Fluent does this. It's very annoying, but in cell zone conditions, if you double click on cell zone conditions here, then you can see your default domain. It's the name of the fluid domain. And by the way, there is an option on the bottom, operating conditions. On the bottom here, there is operating conditions, where you need to set an operating pressure. So this is like the let's say the gauge pressure that you are setting. Since we want to work with gauge pressures equal to absolute pressures, so that in a way that this is our absolute pressure, we need to set this to 0. And okay. If you don't do that, then when you're setting this pressure at the inlet, then you get like the actual pressure is the sum of this plus the atmospheric pressure. So you get an offset. Then in the next, we can double click on boundary conditions. Here we have different surfaces. So let's start from the top. There is default interior. This is an interior type, so it's not really a boundary condition. We can leave it as it is. Then we have the far field. That is the surface on the top. We said we can set this like a symmetry in a way that it doesn't affect the flow. So it's a type symmetry, it's already there, and we are fine with that. Inlet. So the inlet here, we said we need to set total pressure and total temperature. So we need to change the type. On the bottom you have the velocity inlet type by default, and you need to change that to pressure inlet. You can see there is that option. If you click on that, then you get this window open where you can set the gauge total pressure. So that's the value that we want to set. So it's 1.02828 bar. So that's 10 to the power of 5. And then there is this supersonic initial gauge pressure. So that's not a real boundary condition, but it's an initial value that you want to set there. And it's good practice if you don't know, let's say already the dynamic pressure or the flow velocity there, that you set it like the same value as the gauge total pressure. Then you can prevent reverse flow or not, doesn't really matter. Since you don't reverse flow, that means that there is flow that is actually exiting the inlet, if you see that you have problems with your simulation, that could be an option to avoid that problem. But in let's say if you set up correctly, you don't have that problem. So we don't need it, and we can hit apply. So we save this modification. Then we can change in the thermal tab over here on the top, also the total temperature. So we said total temperature 300 Kelvin. This is the one already here by default, so we don't need to change it, and we can close this. So now we set the inlet. So now we need to do it for the next one. Is outlet. The outlet is a pressure outlet. That's correct, since we need to set the static pressure of the outlet. But we can click Edit on the bottom in order to set the gauge pressure. So the value of the static pressure at the outlet. That is 1 bar. So 1 F5, that means 10 to the power of 5 pascals, so 1 bar. Also in this case you can prevent reverse flow, but you don't really need it. And in thermal you can see, let me apply first so that it will save that option. In thermal you can set also the backflow total temperature. So you don't need to set a temperature boundary conditions for this case. This is just the value of the temperature if in case of backflow. So if there is any backflow, that's the value that Fluent will use. But we will not have backflow, so that doesn't really matter. Then we move to plate. So plate is the solid adiabatic wall. Edit. Here we can set in the momentum tab that this is a stationary wall, so it's not moving. And then the shear condition. We said this is a no-slip wall, since the relative velocity between the fluid and the wall is 0. So we leave it as it is. Instead, in thermal tab, we can set thermal conditions. We said that this is an adiabatic wall, so that means that heat flux is equal to 0. So then the option heat flux, and then the value here has to be 0. So that's already by default, and we can close. Then we have symmetry at the inlet. So the first part over here before the plate on the bottom. For other turbulence model, setting it like a symmetry is fine. For this mixing length, apparently no. It messes things up with the inlet boundary conditions, so we set it like a slip wall. So we do that by changing the type. From symmetry, we go to wall. So we select wall type, but of course we don't want shear forces on the flow in that region. So we need to set it like a slip wall. That means that we can change the shear condition to specified shear, and then we set the shear stress equal to 0 for the 3 components. That means that this wall is not accepting any shear stress on the floor. And it applied. Finally, we have the symmetry sides. In the 2D case, of course, you don't see this. So we have only one domain. But in the 2D, in the 3D, we need to set this surface and the parallel one. And we set them like symmetries, so that there is no real forces exerted on the flow, that just the fluid is flowing in that direction, in the parallel to the plate. So we don't change that. Were you all able to set the boundary conditions? I take it as a yes. Yes. Sensitivity to 0, because this is like an offset for the gauge pressure for the output. So if you all are at this point, then we can move on. We can skip most of these setup options, and then we can go then to solution. So how we get the solution of the problem. So in methods, here we can choose some numerical scheme. It's not a purpose of this course, let's say, to explain what these are. So we are just going always, let's say, most of the times with the default options. I use this coupled option. This is coupling the pressure and velocity. I don't really touch any of these spatial discretization. Depending on the version, this may be slightly different. For example, this flux type, maybe in the version you have on this computer, it's not really like that. But it doesn't matter. You can leave it like it is by default. It shouldn't pose any problem for this case. And then the thing that in this version it's like this, so the pseudo time method, I use a global time step method. So what this means is that I'm solving the governing equation, so continuity, momentum, and energy, in a transient form. So I have a transient form, a transient term in the equations, but it's not a real transient, it's just how the solution is iterated, so how the iteration is going towards a steady solution. So we are going solving the transient formulation of the governing equation. Otherwise, you can also set it to off, and then you have a different formulation, so how you get to the steady. Typically, this is quite convenient for most cases. This doesn't require many iterations, it's quite fast, and so then we'll go for that. So we didn't change anything here. You can go to controls. Here you can set some relaxation factors if you wish. Typically, you play with these factors if you see that you can't get a convergent solution, so maybe you play with them. We can leave them as they are. And something that, okay, so now we set the methods and controls. What we can do next is to set the how we get to convergence. So how we define convergent solution. So CFD, of course, it's iterating. We have iterations that for each iteration we get closer to the final solution, and we need to monitor how we are advancing, how our solution is advancing. We can do that, for example, by in record definitions. You can monitor. So here I have new flux report, mass flow rate. So what this means is that I can create a report for the mass flow rate, and I can select the surfaces. So of course, when I get to convergence, that means that the mass that is entering at the inlet is the same mass that is exiting the outlet. If you don't have that condition, that means that your solution is wrong, because then you are breaking like a physical law, that is the continuity equation. So we need to check that this is true, so we can create this report definition. I call it mass imbalance. And I can select the surfaces where there is fluid entering or exiting this surface, so inlet and outlet. Then here you have the options to create a file or a plot. I don't really need a file, so I can just report a plot in a way that while it's solving the equations, it's showing the mass imbalance per iteration. And okay. And close. Then the next thing is in monitor. If we expand that, you see that there is residual. So if you double click on residual, you can set the criteria for which you say, okay, now I got convergence. So residuals of the equations are typically a good way to monitor convergence. Now you don't need to know exactly what they are for this course. You can just trust me somehow and set them to a low value that 10 to the power of 5, it's fine. 10 to the power of minus 5. So I set all of these to this value. So I can say that when the residuals of the solution are that low, then the solution can stop because I have a convergent solution. And okay. Okay, so we have done everything. So the first thing now that we need is to initialization. On the left, we can double click on this. We need to initialize the flow variables in the domain. We can do this in two ways. There is an hybrid initialization that is kind of automatic based on the boundary conditions that you have set. The solver kind of initialize it like a black box. You just don't see what's happening. Or a standard way to initialize it, where you can actually set the pressure, velocity, and temperature in the domain. We are fine with the hybrid. We don't need to check what's happening. We can just let it happen, and if I hit initialize, then you can see there is some iterations. Sometimes this works fine, sometimes no. So we can check if this worked fine. So now we already initialized the domain, so we have flow variables in the domain, and we can plot them. So for example, in results, graphics, we can expand this graphics section, and there is contours. If you double click on contours, then you can, for example, select all of the surfaces, and you can plot one variable for all the surfaces. So let's plot, for example, in the description of the case, we said that the Mach number has to be equal to 0.2. That's, let's say, the one thing that we need to check, that we are running with a Mach number in the free stream region equal to 0.2. So at the end of the solution, we need to check that we get that correct. But right now we can plot the Mach number for the hybrid initialization. So you can select contours of velocity, and then in the second row here, instead of velocity magnitude, you can plot the Mach number. There is that option. And save display. The colors are not really nice. Typically I changed them in view. There is this option lighting. I deselect that option. So now that looks better. Okay, so this is the initialization of the case. There is basically I I change this to float. So we get low Mach number in the domain, and there is like Mach number 0.5 close to the plate. But this is just as initialization. Now we can run. So we can go in the solution, run calculation. Then you can set the fluid time scale. There is option if you want to set an absolute time scale, so you want to set actually the time step of the solution, or an automatic if you trust Fluent to do that. So we will go for that option. And the number of iterations we need to change. We can set it to 1000, it's more than enough. And then I can run the case. So you see that you have two new tabs now: the scale, the residuals, how they are evolving in per iteration, and the mass imbalances. So of course this has to go to 0. You see that at the beginning we have a lot of mass that is probably exiting, it's negative domain, and then we get to 0. And solution converge. So that means that our residuals, all of our residuals, are lower than 10 to the power minus 5. So we got a convergent solution. Were you able to run the case? Do you have problems? Yes? Okay.
I get wrong result. I get no convergence.
Yeah, it's the other side. That's the why. I switched to the left hand. I don't know how to rotate this.
Yeah, do that. Yep.
I couldn't set up the mic. I couldn't even open it. From here, there's no option for
Okay, so this is for CFX. First, you need to create a new case. So when you have then this general, okay. So when you do that, then you have this interface where you can then import the mesh.
I get which convergence somehow.
Okay.
Until 1000.
Okay, there is something. At the beginning, okay. So there's
But this also do.
Uh,
Go please go what see what it is.
then
I don't even know what you're saying. It's supposed to, it's not supposed to look like that. I remember the previous one and the one. Okay, then go back, go down here. Let's see this right. No, it's zip file. Okay, let's see what it is. What I do. Okay. Let me try that. No, Dinesh, you learn it. Let me try.